Hello, students. So, in the previous session, we started talking about the coaxial line. So, we tried to derive what is a dominant mode. We saw that transverse electromagnetic wave propagates on a coaxial line, and that is a mode which we are very much interested in because we know that a TEM wave can have many advantages compared to a non TEM one because a TEM wave does not have any dispersion. Its phase velocity is independent of the frequency. Its field, the shape of the field or the pattern of the field is not going to change with frequency. Uh, and you can deal with voltage and currents if you're dealing with transverse electromagnetic waves. So even we can apply transmission line theory. So there are some quite a bit of advantages if you're dealing with the TM wave. But we saw that the next higher order mode that comes into picture is TE11 mode, and we had the cutoff frequency formula for the TE11 mode. So from here, I can derive the cutoff frequency formula. So this is the cutoff wave number. So if you ask me what is a cutoff frequency, it simply I can write it as omega. Uh, so when k is exactly equal to kc, that is when you have the cutoff frequency. So I can say 2 pi, uh, maybe. Okay, so 2 pi fc times a square root of mu naught epsilon naught and the square root of mu r epsilon r, where kc is nothing but 2 by a plus b. So this is right. So okay. So from here I can cancel out 2 and 2, and I can say fc is nothing but 1 by a plus b times square root of mu r epsilon r, and I have 1 by square root of mu naught epsilon naught, which I can write it as c, velocity of light. Right, so this is the expression for your cutoff frequency for this. So this is the highest mode at which you can operate, because beyond this cutoff frequency, what happens is higher order modes will propagate. So this is the band in which usually a coaxial cable operates. So in the last class we see that this ratio basically depends upon things like sorry, I forgot pi previously in my derivation. So here you had a pi also. Okay. So uh, we saw that you can see the cutoff frequency basically depends upon the value of A and B. Okay. So I can say that if I make a if I take a coaxial cable, okay, means if I make the coaxial cable smaller and smaller, okay. Say for example, if I take uh, a smaller cable, okay, smaller inner cable, or I take a bigger one. Okay, say if I maintain the B by ratio. So in both cases, which one will have a higher cutoff frequency or not? So say for example, let me take a scenario where the B by A ratio is exactly equal to 2. Okay. So say let us have a scenario that the ratio of the outer radius to the inner radius is equal to 2, and say the inner one is, in one case it is 1 mm, and say in another case the A is taken as maybe a bigger one, 5 mm. Okay. So in both cases B by ratio is taken as same. Okay. If in that scenario the cutoff frequency for the first case is nothing but c divided by pi times of, let us say it is an airfield. So I'll take mu r and epsilon r is equal to 1. So of a plus b is 1 plus b is 2 times of a. So you get 2 mm. Okay. So it is basically, so if we calculate this, what we'll get is, so let me do it. So you have a pi here. So 3 into 10 to the power of 8 divided by pi into 3 into 10 to the power of minus 3. So I can see 1 divided by pi. Okay. So I'm getting it around 31.83 gigahertz. So that is the cutoff frequency in case of A. So let me take a case where A is 5 centimeters. Then FC is what? FC is C divided by pi 5 plus 2 times of 5, right? Mm again. So what happens is you get the same, but if you substitute these things, I think for that you get an answer divided by 5. So that will be 6.366 gigahertz. Okay. So you can see that if I go to larger and larger, means say for example the b by ratio is maintained as 2. So means this is 1 mm and this is 2 mm, but whereas this is 5 mm, okay, and this is 10 mm. So it's a larger coaxial cable compared to this one, right? This one is a larger one. And if you see that for the larger coaxial cable, means for this case, the cutoff frequency is lower. Okay, so if you want to have a coaxial cable, so say for example, if I want to operate this, if I want to have a coaxial cable which works in the frequency range of 10 gigahertz or so, then I cannot use this cable, right? Because why can't I use this? Because for this, the cutoff frequency is 6.3. That means if I operate it at 10 gigahertz, then in the coaxial line, both TEM wave and TE wave, TE11 mode also propagates. So which is not desirable to have two modes. So what we do is instead of considering a wire which is having 5 mm, then you need to go for a wire which is a smaller one. Okay. So that is the thing which we saw previously. So for a given value of B by ratio, the value of A decides means what kind of cutoff frequency you're dealing with and all, right? So I think we talked about this in the previous class. In fact, in the previous class we were talking about so what value of B by A is a good enough one. Okay, so which, so you can see that before I have fixed the B by ratio and I have taken the different values of A. So what is this ratio? What ratio actually B by ratio? What value I can take? Obviously, I cannot take B by A is equal to 1 because if I make B by exactly equal to 1, there is no coaxial region. So B by A should be greater than 1. And what should be the what is a good efficient value, right? So that is decided by what kind of characteristic impedance I want and what is the amount of power handling capability I need and what is the attenuation constant that is feasible. So if we look at these properties, then we can decide what is the best value we can choose for the B by ratio. Okay, because the B by ratio basically decides what is your characteristic impedance. We have already derived the expression for characteristic impedance, and we got the answer of that. The characteristic impedance is nothing but eta. Eta is the intrinsic impedance of the wave that is propagating inside the medium. That is, eta is square root of mu by epsilon. In case if it is filled with air, then it is simply 120 pi, right, or 377 ohms. So here Z naught is depending upon the B by ratio, right? So for a given B by ratio, what we decide is means if I choose B by A is exactly equal to 2, then I'm fixing a characteristic impedance. By choosing various values of B by A, obviously B by A should be greater than 1. So say I can choose B by A is equal to 1.5, or I can choose B by A is equal to 1.2, or B by A is equal to 2. So I can choose different values of B by ratio. So what changes when I change the B by ratio is the characteristic impedance changes. So how means how does that affect us? How does this characteristic impedance affect us? And we know already that on a transmission line, characteristic impedance definitely plays an important role, right? So what Z naught you take and what ZL you take, right? This all matters because you need to match the things. Okay, so what characteristic impedance is a good one, right? So definitely what characteristic impedance is better to choose. And uh, or what b by ratio we have to take. Of course, we can have various loads because the value of the load is not in my hand. Definitely I can choose any value of load. So if I have to match it to the characteristic impedance of the line, then I can choose one particular load which is exactly equal to z naught, but that is not in my hand. So choosing a z naught is also not in my hand. So what value of z naught is more feasible in terms of giving a good power handling capability and a good attenuation constant? That is what we are going to answer, right? Because ante, సో ఇఫ్ ఐ చూస్ బీ బై రేషియో ఇస్ ఈక్వల్ టు 1.5, ఈ 1.5 చూస్ చేసుకుంటే నాకు మంచి పవర్ హ్యాండ్లింగ్ క్యాపబిలిటీ వస్తుందా, లేకపోతే గుడ్ అటెన్యూషన్ కాన్స్టెంట్ అంటే తక్కువ అటెనేట్ అవుతూ సిగ్నల్ వెళ్తుందా లేదా అన్నది చెక్ చేసుకోవాలి. ఆర్ బీ బై రేషియో 1.2 తీసుకుంటే నాకు మంచి పవర్ హ్యాండ్లింగ్ క్యాపబిలిటీ ఉంది, లేకపోతే గుడ్ అటెన్యూషన్ కాన్స్టెంట్ అంటే ద వేవ్ ఈజ్ అటెనేటింగ్ లెస్ అని నాకు తెలిసింది అనుకోండి. ఓకే, అయితే బీ బై ఏ రేషియో 1.5 కంటే 1.2 ఈజ్ బెటర్ బికాస్ 1.2 గివ్స్ మీ గుడ్ పవర్ హ్యాండ్లింగ్ క్యాపబిలిటీ. లేకపోతే if I take b by is equal to 2, that gives me less attenuation constant, the wave can propagate a longer distance. సో అట్లాగేంటి అంటే ఫర్ వాట్ రేషియో ఆఫ్ p by ratio I can get good power handling capabilities or attenuation constants. So what is a power handling capability is like how much power you can actually transmit from one location to another, because usually you use this coaxial lines to connect. Say there is an antenna here and your receiver is somewhere, your transmitter is here somewhere, so you have an amplified the signal and you want to send this RF signal through some cable and you want to give it to your antenna. Usually your antenna is not present right beside your circuit. Say for example, if you think of mobile stations, your mobile antenna is at the top of the tower and your circuitry is somewhere at the bottom, right? So you need to transmit, means the signal has to go from one place to another place. Maybe the receiving signal will have less power, but usually a transmitting signal usually has a very high power, because the power is definitely affects uh, how much distance you can cover, the coverage and all. Of course there are multiple factors for the coverage, but definitely the more the power you send, the more coverage you can get for your signal, right? So power always plays a factor, and you want to pump as much as power sometimes communication purpose. So does your coaxial line, this connecting wire, have that capability? అంటే ఎక్కువ పవర్ పంపించాం అనుకోండి, మేబీ ఆన్ ద లైన్ a lot of voltage develops or huge currents flow, and because of that the wire can burn out. ఓకే, కాలిపోయే ఛాన్సెస్ ఉంటాయి. సో వాట్ ఈస్ అ బ్రేక్ డౌన్, రైట్? దట్ డిసైడ్స్ వాట్ ఈస్ ద క్యాపబిలిటీ ఆఫ్ ద వైర్, ఎంత పవర్ హ్యాండిల్ చేయగలదు అన్నది. అట్లానే అటెన్యూషన్ కాన్స్టెంట్ ఏం చెప్తుంది? సో వెళ్తున్న సిగ్నల్ యూ మైట్ గివ్ సో లాట్ ఆఫ్ పవర్ అట్ ద ఇన్పుట్. ఇక్కడ బోల్డ్ అంత పవర్, ఒక 1 watt పవర్ ఇచ్చారనుకోండి, యాంటీనా దగ్గరికి వెళ్ళేటప్పటికి ఈ లైన్ అన్నది సే ఇఫ్ ఇట్ ఈస్ ఈటింగ్ 0.9 watt ఆఫ్ ద పవర్, బట్ ఎట్ ద యాంటీనా యూ ఓన్లీ గివ్ 0.1 watt. సో దాన్ని కెన్ ఐ యూజ్ దిస్ కేబుల్ అంటే ఇట్ ఈస్ అ వర్స్ట్ కేబుల్, అంతే కదా? అంటే 1 watt పవర్ ఇన్పుట్లో ఇస్తుంటే యాంటీనాకి 0.1 watt ఇస్తుంది అంటే there are huge amount of losses in the cable. So that is not a good way to design a cable, right? So the question here is, what is a good design for the cable, right? So to understand that, first of all we need to have expressions for what is the power handling capability of a coaxial cable and what is the attenuation constant formula for the coaxial cable. So let us first try to derive the expression for maximum power handling capability. So we know that the maximum power handling capability is decided by when the dielectric can break, right? So usually there is a dielectric medium between. So here there is one conductor and there is another conductor here. So what happens? There is some potential difference. So there is electric field between them. So there is some dielectric between these two conductors, and once your electric field strength, the strength of the electric field, okay, or the magnitude of the electric field, when it crosses a certain value, దాన్ని ఏమంటున్నాము? డైఎలక్ట్రిక్ స్ట్రెంగ్త్ అని పిలుస్తున్నాం. We call it as dielectric strength. Like for example, air has a dielectric strength of around 3 into 10 to the power of 6 volt per meter. అంటే ఇంతకంటే ఎక్కువ ఎలక్ట్రిక్ ఫీల్డ్ స్ట్రెంగ్త్ అప్లై చేస్తే ఎయిర్లో ఎయిర్ బ్రేక్స్ డౌన్, right? So instead of working as an insulator, it starts to behave like as a conductor or it breaks down, right? So dielectric breakdown జరుగుతుంది. so that can disrupt your communications and all. So, and even it can damage the device. So for every material that is present in the middle, it will have a strength, some ED అన్నాం. ఓకే. సో అంటే ఇంతకంటే ఎక్కువ ఎలక్ట్రిక్ ఫీల్డ్ వచ్చిందంటే ఇట్ విల్ బ్రేక్ డౌన్. అయితే ఇన్సైడ్ యువర్ కోయాక్సిల్ కేబుల్, the electric field expression we have already derived it. We got the expression for electric field like this. If the potential is V naught, we have the expression for electric field as V naught by ln of B by A 1 by rho e power minus j beta z rho cap. I think you can see that their electric field has a rho dependency. Rho and ante. Rho is what? Rho is from your cylindrical coordinate system. It is nothing but the perpendicular distance from origin. So this radial distance. So as you go far and far away, because it's inversely proportional, your electric field strength is going to decrease. So obviously, you have one conductor. Inside the conductor, the electric field is zero. And once you start from here, I can see that at the boundary here, okay, the rho is going to change from A to B. So where can I have the maximum electric field is, it depends upon where I have the smallest radial distance. So where I have the smallest radial distance, there I can have the maximum electric field. You might say the smallest radial distance is rho equal to 0, but rho is equal to 0 is not a case here, because your coaxial cable itself starts from rho is equal to A to rho is equal to B. So A is the smallest number. So I can say that the electric field is maximum. So this is the magnitude. So if I write the magnitude is V naught by ln of rho by A into 1 by rho. So if you ask me what is the maximum electric field I can get, is the electric field magnitude is maximum when rho is equal to A. Right. So if I put rho is equal to A, so then the maximum electric field I can get is ln of B by A, right? 1 by A. Rho plus A substitute chesam. So I can see that when this factor becomes exactly equal to the dielectric strength I'm talking about, if it is exactly this maximum electric field, a dielectric strength equal అయిందనుకోండి, then that means that is the place where the breakdown happens. Or because V naught is what we are calling as the voltage between the lines. So from here I can write V naught, or that maximum voltage is nothing but, I can take this to the other side. It simply becomes ED into A into ln of B by A. So for a given dielectric medium, if I know the value of ED, and if I know the value of A, and if I know the value of B by A ratio, then I can easily find what is the maximum value of voltage I can apply between the lines, so that it will not break down, right? So that is the maximum value before a breakdown can happen. So if this is the maximum voltage that you can apply, then what is the maximum power you can have? Because this is nothing but a transmission line. So on your transmission line, the time average power is nothing but voltage square divided by 2 times of the characteristic impedance Z naught. So if I substitute that, you can see that the formula for the maximum power handling capability is pi a square ed square by eta into times of ln of b by a. So if you look at this, previously what we saw is, if I had a cable, so I took a cable like this. If you remember, I take a cable of 1 mm, okay, inner cable of radius 1 mm, and I have taken a cable which is of inner radius of 5 mm, right? So 5 mm this column. So for 1 mm, the cutoff frequency I think was around 39.8 gigahertz or so, and for the 5 mm one, the cutoff frequency was around 5, I think 6 point something 8 gigahertz or so, right? So if I had a case like this, so now if you ask me which one will have the maximum power handling capability, so let us take a scenario where it is air filled, okay, and still the B by ratio is taken as 2 in both cases. So if it is 2 in both cases, so let me try to find what is the power handling, which one has the good power handling capability compared to the other one, right? So if you see that for A is equal to 1 mm case, okay, so it is pi. So let us take it as air filled, okay, so 1 mm square, so it is 10 to the power of minus 3 whole square, and let me take ED as therefore it is air filled. So then it is 3 into 10 to the power of 6 whole square divided by, because it's air filled, it is 120 pi, and ln of b by a is taken as 2. Okay, so I can cancel out pi and pi here, and I can see I have 10 to the power of minus 6 into 9 into 10 to the power of 12 into ln of 2 divided by 120. Okay, so the answer is 9 into ln of 2 divided by 120. So maybe I can multiply it with the 1000 here. Okay, so I'm getting it around 51.98 kilowatts. So this is the maximum power you can handle. Okay, so this is the maximum power I got. So if you want the maximum voltage, so this is the P max. Okay, so let me calculate the V max also in this case. So the V max is 3 into 10 to the power of 6 into A is 1 mm into ln of 2. Okay, so it's 3 into ln of 2. So I'm getting the answer as 2.07 kilovolts. Okay, so this is how much you can apply if it is a 1 mm cable and it is air filled B by ratio. So let me take a scenario where it is uh, filled with 5 mm cable. So if it is a 5 mm cable, so if you write, so this is for A is equal to 1 case. So if I had to do it for, excuse me, if I had to do it for A is equal to 5 mm case, so I get the formula again as pi times of, now I have 5 mm, so I have 5 square into again 10 to the power of minus 3 whole square into ED is 3 into 10 to the power of 6 whole square, and ln of b by a is ln of 2 divided by eta is 120 pi. So you can see that I have the same expression, but instead I have a 25 square extra here. So if I have to do that, it is 51.98 into 25, right? I get the maximum power I can deal now is 1299.5 kilowatts. Okay, but whereas what is a Vmax I can get, what is the maximum I can get is, so in that case it is again 3 into 10 to the power of 6. Now you have 5 into 10 to the power of minus 3 into ln of 2. Okay, so it is 5 times more than the Vmax here. So it is 2.07 into 5. So it is 10 point. So 10.35 volts, kilovolts. So I can see that compared to a 1 mm cable, a 5 mm cable or the broader one, okay, or the bigger one is actually having a very good power handling capability. It can actually deal with very high power or very high voltage compared to a thin wire. But the problem is for A is equal to 1 mm, the cutoff frequency is very small. So అంటే ఇక్కడ higher order modes చాలా త్వరగా వచ్చేస్తాయి. For A is equal to 5 mm, the cutoff frequency is very small. So what happens, the higher order modes comes very faster, but this has a very good power handling capability. అంటే దీనికి మంచి పవర్ హ్యాండ్లింగ్ క్యాపబిలిటీ ఉన్నా కూడా హైయర్ ఆర్డర్ మోడ్స్ వచ్చేస్తాయి. సో దెర్ ఇస్ అ ట్రేడ్ ఆఫ్ నౌ, యూ కెన్ సీ. సో ఇఫ్ యూ టేక్ ఎ బిగ్గర్ వైర్ విత్ ఇన్నర్ రేడియస్ బిగ్గర్గా ఉన్నది తీసుకున్నాం అనుకోండి, అలా తీసుకోవడం ఫర్ ఎ గివెన్ వాల్యూ ఆఫ్ బీ బై రేషియో, ఇఫ్ ఐ టేక్ ఎ బిగ్గర్ రేడియస్ వాట్ హ్యాపెన్స్ ఈజ్ I get more power handling capability, but the cutoff frequency is lesser. But if I take a smaller one, the power handling capability is less. Then I have to, but I can operate it at very high frequencies also in a TM wave, right? So these are the things which you have to deal with. So we have the expression for power handling capability. Okay, so I can say the larger coaxial cable, you get maximum power handling capability, so which we saw actually. But the problem is, if I take a larger cable, higher order modes will come into picture. Means the cutoff frequency becomes smaller and smaller, so higher order modes will be coming into picture. Okay, and moreover, the power handling capability which we derived is done with an assumption that it is air filled. First of all, ఆఫ్ కోర్స్ ఇట్స్ ఎయిర్ ఫీల్డ్ అని మనం తీసుకొని సాల్వ్ చేసాము. బట్ ఇక్కడ ఈడీ డిఫరెంట్ వాల్యూస్ ప్లేస్ చేయొచ్చు. కానీ నాకు వచ్చిన పవర్ హ్యాండ్లింగ్ క్యాపబిలిటీ ఏంటి అంటే, దిస్ ఈజ్ అస్యూమ్డ్ దట్ ఆన్ ద లైన్ దెర్ ఆర్ నో రిఫ్లెక్షన్స్. సో దెర్ ఈస్ ఓన్లీ వన్ వేవ్ దట్ ఈస్ ప్రాపగేటింగ్. But if there are any reflections, and if say you use this coaxial line, so here is your source, so this is your transmitter, and here you connected it to an antenna or something, right? అయితే say for example, if the load is mismatched, so here the impedance is Z naught, but here the load is ZL, so there is some reflection. So what happens if there is a reflected wave? You have a standing wave. So then the maximum value of voltage on the line is nothing but V naught plus into 1 plus the reflection coefficient, if you remember, right? So so we don't know what is the value of V naught plus, but I can say that the maximum value of the volt can increase beyond what you expect. అంటే ఒక సింగిల్ వేవ్ వెళ్తున్నప్పుడు ఉన్న వోల్టేజ్ కంటే రిఫ్లెక్షన్స్ ఉన్నప్పుడు, because of the reflected wave or because of the standing waves, what happens is the voltage that you get on a line can increase. Okay, so say for example మనం ఏమనుకున్నాం అంటే, right, like for example in the previous calculation which we have done, సో సే ఫర్ మనకి ఇక్కడ మాక్సిమం వోల్టేజ్ 2 kV వచ్చిందన్న. ఓకే, సో హ్యావ్ ఏ 2 kV. సో నేను ఏం చేశానంటే, బికాజ్ ఐ కెన్ ఆపరేట్ దిస్ 1 mm వైర్, ఒక 1 mm వైర్ తీసుకుంటే ఆ వైర్ని నేను 2 kV వరకు ఆపరేట్ చేయొచ్చు కాబట్టి, సో ఫర్ ఎగ్జాంపుల్ అంటే ఈ వైర్ మీద ఇఫ్ ఐ సెండ్ ఏ 3 kV సిగ్నల్, దెన్ ఇట్ విల్ డెఫినెట్లీ బ్రేక్ డౌన్. సో అందుకని ఏం చేశానంటే, ఇన్స్టెడ్ ఆఫ్ యూజింగ్ 2 kV, ఐ విల్ సెండ్ 1 kV సిగ్నల్. సో ఈ వైర్ మీద ఒక 1 kV సిగ్నల్ పంపిస్తున్నాను. పంపిస్తే బ్రేక్ అవుతుంది. విల్ దిస్ వైర్ బర్న్ ఆర్ ఇట్ విల్ బ్రేక్ డౌన్ అంటే, ఇట్ విల్ నాట్. ఇట్ విల్ హ్యాపీలీ సెండ్ ద సిగ్నల్. బట్ ద ప్రాబ్లమ్ ఈజ్ ఇఫ్ దెర్ ఇస్ రిఫ్లెక్షన్. Say for example, some signal is reflected back, and because of that, there is an exact equal and opposite reflection. Because of that, the maximum voltage can reach 2 kV. Okay, or say in 1.5, 2 కాదులే 1.5 పెట్టుకున్నాను అనుకోండి. If I send 1.5, then if there is a exactly వచ్చి వెళ్తున్న సిగ్నల్ రిఫ్లెక్ట్ అవుతుంది అనుకోండి బ్యాక్కి, మేబీ a thing can happen like the total voltage, the maximum voltage you can see on the line can double. It can become 3 kV. డబుల్ ఎందుకు అవుతుంది సార్ అంటే, బికాస్ నువ్వు పంపిస్తుంది 1.5 kV సిగ్నల్ని. ఓకే, రిటర్న్ ఫర్ ఎగ్జాంపుల్ ఒక రిటర్న్ వస్తున్న సిగ్నల్కి కూడా 1.5 kV ఉందనుకోండి. అంటే నువ్వు పంపిస్తున్న సిగ్నల్ ఎగ్జాక్ట్గా కంప్లీట్గా రిఫ్లెక్ట్ అయ్యి వెనక్కి వచ్చేస్తుంది అనుకోండి. At some point, they can add constructively. At some point, the forward wave and backward wave can add constructively, and the total voltage on the line can become now 3 kV. మేబీ యు ఆర్ సెండింగ్ అంటే నువ్వు పంపించేది 1.5 kV, దానివల్ల వైర్కి ఏమి అవ్వదు అనుకుని పంపిస్తున్నావు. బికాస్ వీ హ్యాడ్ ఎ లిమిట్ దట్ 2 kV కంటే తక్కువ పంపిస్తే ప్రాబ్లం ఏం లేదు అని చెప్పాను. సో 2 kV అయితే మ్యాక్సిమం యూ కెన్ అప్లై అంటే, మీరు ఓకే అయితే నేను 1.5 అప్లై చేస్తాను అని పంపించారు. But what happened, because you didn't match it properly, the reflection can happen, and because of these reflections, the maximum voltage can double, right? So what happens now? So instead on the line with put 3 kV unnattu, which is very much higher than the 2 kV, so it will break down. Even though you are sending a signal which is 1.5 k only, because of these reflections, unexpectedly the maximum voltage can change. So you should be careful about that. So అందుకని ఏంటంటే, though the maximum power handling capability is derived without assuming without any reflections, but with reflections the thing can change. So practically use చేసేటప్పుడు ఏంటి అంటే, so because of the reflections, the power handling capability is usually treated as a reduced one. అంటే యూజువల్లీ ఏంటంటే ద డిక్రీజ్ ఇట్ బై పవర్ ఫ్యాక్టర్ ఆఫ్ 4. అంటే ఫర్ ఎగ్జాంపుల్, అంటే లైక్ వోల్టేజ్ కెన్ బి, సో ఇక్కడ నేను 2 volts తీసుకుంటున్నాను అనుకోండి. సో ఐ విల్ సే ఇఫ్ దిస్ ఇస్ ద Vmax, this is the derived one. Okay, so this is the derived maximum voltage for 1 mm. బట్ ప్రాక్టికల్‌గా ఏం చేస్తారు? ప్రాక్టికల్లీ Vmax ఈస్ గివెన్ యాస్ ఓన్లీ 1 kV. అంటే 1 kV కంటే ఎక్కువ అప్లై చేయకూడదని చెప్తారు. అదేంటి సార్ మనం రిజల్ట్ డిరైవ్ చేస్తే 2 కిలోవోల్ట్ వస్తది కదా! అంటే అవును. అది ప్రాక్టికల్‌గా అయితే అది డిరైవ్ చేస్తే థియరిటికల్‌గా 2 కిలోవోల్ట్ దాకా వాడొచ్చు. అదెప్పుడు డిరైవ్ చేసామంటే వి డిరైవ్ ఇట్ విత్ అన్ అజంప్షన్ థట్ దేర్ ఆర్ నో రిఫ్లెక్షన్స్. So we don't know whether there will be reflections or not. So it's always better to use it practically with a half value of it. So ఇక్కడ 1 కిలోవోల్ట్‌కే నేను మాక్సిమం అంటాను. అంటే 1 కిలో కంటే ఎక్కువ అప్లై చేయకూడదు. సో అంటే నేను ఫర్ ఎగ్జాంపుల్ ఇఫ్ ఐ అప్లై 0.5 కిలోవోల్ట్ will there be any dielectric breakdown అంటే there won't be. Okay, because even there is a complete reflection, the maximum it can go is 1 kilovolt and nothing can happen. So if this is voltage, so if I say the voltage is taken as half, the power handling capability is decreased by factor of 4 because square వస్తది కాబట్టి. Okay, so you can see that there are some practical limits definitely. Even if I take a bigger and bigger wire, for a bigger wire the cutoff frequencies are damaging, but and you cannot operate it at very high frequencies though you have good power handling capability. But if a wire which you can operate it at very high frequencies, you need to take a smaller coaxial cables. But for smaller coaxial cables the power handling capability will be very less. So even the practical power handling capabilities becomes lesser and lesser, right? So this is all about the power handling capability. If we had to talk about what is a uh, attenuation constant we face, means what is the value of means you can have various kinds of attenuations, right? You can have attenuation because of the dielectric losses, or you can have attenuation because of the conductor losses. Right now we are not dealing with the attenuation constant because of dielectric losses. That is a will only take into account that the conductor is a lossy one. Say for example the conductors that are using in your coaxial cable are a lossy materials, then what is the value of alpha c? So the method in which we have to calculate this alpha c is not a new one to you. Okay, we have already uh, done it. We have calculated the value of alpha c attenuation constant in the rectangular waveguides also for T10 mode. So the alpha c you can calculate it as PL divided by 2 PT. If you remember, PL is the power that is lost per unit length. Okay, and PT is the power that is transmitted through this transverse plane. So in the transverse plane, how much power is passing through. So we have the value of electric field inside your coaxial line. So how do you calculate the power that is transmitted? అంటే ఈ రీజియన్లో పవర్ ఎంత ట్రాన్స్మిట్ అవుతుందో అనేది కావాలి. సో ఇన్ దిస్ రీజియన్ you can see the average power is modulus of E square by 2 eta into ds. So in this region, because the region in which I have shaded, a shaded region low, what is changing? In the shaded region, what is changing is uh, because this region, I can say ds bar as the rho is changing, right? The rho is changing and phi is also changing. So you have rho d phi, rho d phi. Okay, and you have the magnitude of electric field and you square it and you have to perform the integration. Rho changes from a to b and phi changes from 0 to 2 pi, and through this region అంటే ఈ షేడ్ చేసిన రీజన్ నుంచి ఎంత పవర్ క్రాస్ అవుతుంది అన్నది తెలుస్తుంది. సో ద వాల్యూ ఆఫ్ దిస్ ఇస్ సంథింగ్ you get v naught square pi into ln of b by a into eta. So now let us calculate pl. Pl is what? Pl is nothing but the power loss per unit length. So per unit length you have to go find the surface currents. Okay, you have to find the surface currents on the top surface, on the top surface of the conductor, and you have to find the surface currents on the inner surface of the conductor, and then you need to perform this line integral on the curves which I have drawn here. ఈ curves మీద line integral perform చేస్తాము. We saw this already in while dealing with the rectangular waveguides. So I have given you derivation how do you get this expressions also. So from here you can actually calculate the the surface currents. The surface currents is nothing but the normal vector cross product of magnetic field at that surface, which is the boundary conditions. So you can get the surface current on the outer one also as minus rho cap of h bar. So you take a minus rho bar here because your normal should be always be pointing away from the conductor. So that is why you had taken a minus rho cap. So With this, you can actually, we have the expression for magnetic field, because if you have the expression for electric field, this is a transverse electromagnetic wave. Simply you divide it by 1 by eta and you write the correct direction here, that is phi cap. So we have the expression for magnetic field, you can substitute and you can get the expressions for the surface currents. So once you substitute, you get the surface currents expression for the inner one and for the outer one. You substitute them in these integrations and you perform the integrations. So you can see the inner surface is changing from 0 to 2 pi, and outer surface also is changing from 0 to 2 pi. And if you perform these integrations, you get the PL factor something like this. So this is PL. So if you want alpha c, you can see the value of alpha c is nothing but rs by 2 eta times of ln of b by a into 1 by a plus 1 by b. Right. So here also, okay, for a given value of b by a, so maybe I can write this expression like this: rs times of 2 eta times of ln of b by a. So if I take uh, 1 by a common here, so I get 1 by a times of 1 by b divided by 1 by a. So you get a by b, or I can write in the denominator b by a like this, right? So I can see that for a given value of b by a, this whole thing rs and all thing is a constant, and you can see it is inversely proportional to a. So I can say that if a is a bigger one, and if our a is equal to 1 mm and b is equal to, or a is equal to 5 mm, ఈ రెండు కేసెస్లో దేనికి ఆల్ఫా సి ఎక్కువ ఉంటుంది అంటే, ఐ కెన్ డెఫినెట్లీ సే ద ఆల్ఫా సి ఫర్ 1 mm is bigger compared to alpha c for 5 mm. So I can say the bigger the wire, the attenuation constant will be lesser. So this is good, right? So power handling capability ki, good power handling capability ki, good attenuation constant ki wire పెద్దగా ఉండాలి. బట్ ఎక్కువ ఫ్రీక్వెన్సీస్ ఆపరేట్ అంటే, if I want to operate a coaxial live cable at very high frequencies, then I have to take a smaller coaxial line. So there is definitely a trade-off. So what is the best fit? What is the best fit of this ratio? So the question is, what value of A basically minimizes the conductor losses? A value of A conductor losses minimize chestadi, and A value of A will maximize the power handling capability. So to know that, so what I'm trying to find is what is the optimum coaxial cable I can get. So to do that, we have an expression here. This is the expression for maximum power handling capability. So the maximum value into తెలియాలి అంటే, I can see that I can write this pi a square ed, and pi into ed eta ఇవన్నీ some constants అన్న for a given value of, for say మనం ఇక్కడ ఏం చేద్దామంటే, we'll take that this medium eta, this is a waveguide, means we are deriving it for a case where it is filled with air filled waveguide ఒకటి air filled coaxial line తీసుకుని, దానికి ఫర్ ఎగ్జాంపుల్ సమ్ కాన్స్టెంట్, యూ కెన్ సీ ద maximum power is proportional to c times of a square of ln of b by a. So if I take the derivative with respect to a, I get 2a ln of b by a minus a square by a equal to 0. So from here, I get that. So 2 times of ln of b by a minus 1 equal to 0, or x equal to, that looks like 2 ln of x equal to 1, where ln of x equal to 0.5. That happens when x equal to 1.65. Or so under b by a ratio, when b by a ratio, 1 second. Right. So when, Excuse me. Small issue with the slides. 1 second, students. Writing that. I think a small issue with the PPT. Right. So we are trying to find the value which the Weaver ratio which can give me the maximum power handling capability, and we got that for ratio B by A exactly equal to 1.65. Okay, and for a given value of A, I can actually have a very good or the maximum power handling capability I can get. Okay, so for a given value of A, to achieve, because what we are seeing previously is by changing the value of A, we are seeing that the maximum power handling capability you can definitely increase or not. But the question is now, if I fix the value of A, and if I want to choose a good what ratio of B by A value, means for a given value of A, the value of A that maximizes the power handling capability is what we are looking for, that B by ratio. So I can see that for the value of A, if I take a B by ratio which is exactly equal to 1.65, then I can have a maximum power handling capability in a given, for a given value of A, right? So that means we know that if I fix a B by ratio, I can fix the characteristic impedance. So if I assume it is air filled for epsilon r is equal to 1, I can say that if I put B by A is equal to 1.65, I can get that the characteristic impedance is approximately close to 30 ohms. So if I design a coaxial line, if it is air filled, an air filled coaxial line which is of characteristics of 30 ohms, okay, will always have maximum power handling capability. So that is what I'm trying to say. So if you design a coaxial line which is having a, which you can, if you can design a coaxial line which is having a characteristic impedance, it doesn't matter what is the value of A of it or not, the Babier ratio I'm saying, if you can design a coaxial line which is of having 30 ohms characteristic impedance, it will definitely have maximum power handling capability. Okay. So what is the minimum? So in order to see what is the minimum attenuation constant I can get, again here also, if I take the derivative with respect to A, and if I try to find their value of this equation, it is something like 1 plus, we need to solve this equation 1 plus x is equal to x into ln of x. It is a transcendental equation. You can find the solution, approximate solution close to, if the B by ratio is close to 3.59, then you can have minimum value of the attenuation. And for that minimum value of attenuation, if I choose the medium is air, then I can see the characteristic impedance is around 77 ohms. That means if I choose a wire whose characteristic impedance is 77 ohms exactly, then I can have a coaxial cable with very minimum attenuation. So the signal will be attenuated very much less. So you can see that by changing the value of B by ratios, I can actually play with the amount of power handling capability I can get, or amount of attenuation I can get. So if I want maximum power handling capability, I need to choose a cable with a characteristic impedance of 37 ohms. If I want a maximum, I mean minimum attenuation, I need a 77 ohms line. Okay, so this is all for epsilon r is equal to 1. Okay. But if epsilon r is not equal to 1, if epsilon r is a finite value, then maybe these values might change. Say, for example, if epsilon r1 is some 2.1 or so, then maybe the maximum power will be around 20 ohms and this will be around close to 55 or some ohms. Okay. So the thing is, usually when we were solving the transmission line questions, or most of the time, you see that always the characteristic impedance is usually taken a number of 50 ohms. So when I was dealing with the transmission lines, I told you that in RF circuits, most of the time, we'll be using a 50 ohm transmission line. And there is a reason behind using 50 ohm, I used to say, because coaxial cable is the most popular one that is used for connecting any two RF devices as a guiding medium, because coaxial cable operates in a transverse electromagnetic wave. Because of the TEM wave operation, coaxial cable is often used for connecting RF systems like antennas and transmitters and whatnot. And the line, the coaxial line, is usually designed for 50 ohm. It is designed for 50 ohm. Of course, the TV cables might be designing for 75 ohm. There is a different reason for it, but the 50 ohm lines are designed more often, and they are used a lot because it is kind of compromise between the maximum power and the minimum attenuation. So if I choose a line which is of 50 ohm, okay, in that case I can have both the maximum power and minimum attenuation combined. Maybe it is not the completely minimum one, but the power handling capability will be good and it will have a good attenuation constant, minimum attenuation constant, so that I can use it for practical purposes. So that is why 50 ohm is kind of compromise between these two. Okay. And moreover, if you can see, uh, if you fill it with some dielectric medium which is polyethylene filled, that is epsilon r is equal to 2.1 or so, then you can see that the minimum attenuation is obtained exactly at 51 ohms or 50 ohms. So usually the coaxial cables are filled with this polyethylene in the middle. Okay, so these coaxial lines which are designed at 50 ohms usually have a very minimum attenuation. So that is good, right? So your coaxial cable is not going to eat a lot of power. Okay, though the power handling capability is not completely good enough one, means it is not the best one, but it is good enough, right? So because if you have a 20 ohm, if you take a 20 ohm line, then it can have more power handling capability. But we usually choose a 50 ohm line. So 50 ohm line is like a compromise between a maximum power and minimum attenuation. Okay. So here are some plots to give you an idea. So by changing the B by A ratio for different values of B by A ratio, what changes is the characteristic impedance. You can see. So this plot here, one axis is Z0 because Z0 is basically depends on the B by ratio. So for a given value of B by ratio, you get different values of Z0. And here what I have plotted is, here particularly we have taken a wire whose diameter is 10 mm inner diameter, or this A is actually 5 mm. Okay, so we took A of 5 mm, and we have plotted the loss alpha C, okay, attenuation constant in dB per meter at the frequency of 10 gigahertz. So it is plotted at a given frequency of C at some frequency 10 gigahertz, and you can see the attenuation for different values of B by ratio. You can see the almost the attenuation constant decreases for if I increase the B by ratio. Okay, and it increase again slowly, but you can see that somewhere here around when your characteristic impedance is 77 ohm, you get a minimum. And you can see this minimum is not a completely a sharp minimum. Okay, it is a kind of a smooth one. So basically you can operate it around any this region, you can still get the minimum attenuation. So that is what you can achieve. Is this a plot between the characteristic impedance of the B by ratio and the attenuation you can achieve. So here is a plot for the maximum power handling capabilities and the maximum voltage also. So you can see for different values of B by ratio or for different values of Z naught. Okay, if it is air filled, if you assume it is air filled, and if you assume that this is the ED value, okay, for the same 5 mm coaxial cable, you can see that the maximum power handling power you can get for different values of B by ratio. So what I have done here is I have taken a value of 5 mm, and I'm changing the B by a value. Okay, so in that B by value I have taken as 2, but I can see that at some value at a point of 1.65 or so, I get the peak. Okay, there I get maximum power handling capability. So basically you can see at 50 it is not the maximum one, but it is okay, right? Compared to the other case, it is okay. So uh, these are the plots indicating what is a good B by A value ratio that you can choose to get maximum power handling capability as well as this thing. So previously we didn't include any epsilon r was only taken as 1. If at all you change your epsilon r, you can see that if I take the attenuation constant alpha c, this is for epsilon r is equal to 1, where you saw the peak was around 77 ohms. But now if you change epsilon r to 2.2, some polyethylene filled or so, then you can see that the minimum attenuation is actually shifted to 50 ohms. Okay, so so by filling the dielectric medium, you can actually means your attenuation constant is changing a bit, or I can say that your attenuation constant is increasing. Okay, and even because of the dielectric losses, you basically get also an attenuation constant. So I can say the 50 ohm is a kind of like an industrial standard which is commonly used for all kinds of circuits. So whenever you design an antenna, microstrip antenna, or you design uh, any kind of RF circuit, you always say, for example, you're designing an amplifier. Your amplifier is designed for an input impedance of 50 ohms and even an output impedance of 50 ohms, usually in RF circuits. So most of the time, your RF circuits are designed for 50 ohms. any low noise amplifier or oscillators, mixers, all these kind of setups are designed for 50 ohm, because a 50 ohm is a kind of common standard, because all the coaxial cables that are used for measurement purposes or for design purposes are usually made out of 50 ohm only. Okay. But of course, the TV cables are made out of 75 ohms. That there is a separate reason for it, because it's something related to antenna design, folded antenna design. Okay, so there they use some transformers, and to have a design a folded antenna, they usually go for this 75 ohms. That is not relevant for your course, but 50 ohm is kind of like an industrial standard that is used a lot. So, so that is an optimum coaxial cable. So you can see that there are various coaxial cables. Usually the coaxial cables are denoted with RG, and with the number RG is nothing but radio guide. Okay. So you can see that here there are various coaxial cables and the corresponding impedance values and the cutoff frequency. Okay. So I guess with this, we have an understanding regarding the coaxial cables. Maybe in the next session, we'll talk about the coaxial connectors and the other planar transmission lines.